So I hope this is visible to you all. Audio video perfect, right? Good. Now let's start. So the first topic is Boolean algebra, right? So in Boolean algebra, see, as we all know, in the computer will understand only the language of zeros and one, right? So how you will represent zeros and one? So we have two logics. In the positive logic, we will represent high voltage, or the logic 1 for the high voltage with the help of high voltage, like it may be plus 5 volt, right? And how you will represent 0? We will represent 0 with 0 volt, right? So plus 5 volt for logic 1 and 0 volt for the logic 0. So this thing is very important. Sometimes examiner can like confuse you just by writing the, okay, you have to consider a positive logic system, or you have to consider a logic negative logic system. So you must know what is the meaning of positive and negative. So in case of negative logic system, it is just opposite of the positive. So to represent logic 0, we will take plus 5 volt. If in the negative logic system, if voltage is plus 5 volt, then so it means that this is going to be logic 0, right? Similarly, for 0 volt will be used for the logic 1. Okay. So next is duality, a positive logic converted into negative logic system. That concept will be known as the duality. So suppose an expression is given to you, then how you will find the dual of that expression? So you will replace or with and, you will replace and with or, you will replace 0 with 1, but the variables will remain same. Like if it is a plus b na, so you will not complement these variables, these are going to be same only, right? So this is the meaning of dual, right? So what is the dual of and gate? The dual of and gate is or, like it is a into b na, so this plus dot will be replaced with plus. So the dual of and is or. Dual of your this thing XOR is XNOR. Dual of NAND is NOR, like this. Okay, if you find it difficult to remember, then just remember this thing. Okay, how you will find the dual. Okay, and what is the meaning of self dual? Self dual means if you will if you followed these three steps, and when you will simplify the resultant, then you will get the same expression that you have before applying these things, right? So that will be known as the self dual. Okay, now next is mean terms. So maximum possible, see, if you have n number of input variables, right? So the possible number of mean terms are 2 raised to power n only, right? Because if you have n input variables, then how many input combinations are possible? 2 raised to power n only na? So for those input combinations, you will have 2 raised to power your this thing possible values of mean terms, right? Next is max term. Again, you can have maximum value of the max term is going to be 2 raised to power n in any system if the total of mean term plus max term will not be greater than 2 raised to power n. Suppose we have three variables, so total number of possible input combinations are going to be 8. So the maximum number of possible your this thing, if we have all the mean terms, then to 8 number of mean terms will be possible. If you maximum number of max terms that are possible 8, but suppose out of 8 3 are mean term, then remaining 5 will be your max term. Okay, like this you can find the number of mean terms and max term. It will not exceed 2 raised to power n, and the sum of mean terms is 1, right? Obviously mean terms, see, if you are expressing your this thing binary boolean expression in SOP form, sum of product form, so we are writing if boolean expression in this form, so we will take the mean term, we will take the input combinations for which your output is logic 1. Okay, so those terms will be known as the mean term, right? and the product of maxterm is 0. So in case of POS form, product of some form, we will consider the input combinations for which output is logic 0. So in POS form you will multiply the maxterms like this. Okay, so these for those input combinations, your this thing output is going to be logic 0. Okay, now here are the few laws to simplify the Boolean expression. See students, why I am quickly see I am see this lecture is for the quick revision, right? It is so here I am not going to discuss the topics from the concepts from the scratch stuff. It is just quick revision session, right? So these are the few identity. With the help of these identity, we will write down the or we will simplify the Boolean expression, right? So the question arises, why we want to simplify this expression. Say students, from the truth table you will write down the Boolean expression, and with the help of Boolean expression you will implement the circuit, right? So our target is to use minimum number of logic gates, right, to implement a circuit, so that the lots of advantages will be there. Area will be reduced, power dissipation will be less, cost will be less, the speed will be more, right? So that's why, to simplify the Boolean expression, these are the few laws that we can follow. And students, there is one thing. See, if you have a any your Boolean expression in its standard form or in its canonical form, so the question arises, what is canonical form or standard form? In canonical form, see the each min term will be each your this thing each term will carry, or each term will be written with the help of all the variables, right? See, if you have three input variables, then all the terms will have three variables, right? So see, if you will simplify your Boolean expression using these laws, so the original expression and the simplified Boolean expression both will provide you the same output, right? Functionality will never change if you are simplifying any Boolean expression, right? So there's few if you will multiply a with 1, then it is going to be a only. If you will multiply a with 0, so this is going to be 0. A into a will be a into a bar will be 0. Why 0? Because see, if the value of a is 0, then a bar will be 1, so it is 0, right? So this is going to be always 0. AB is equals to b. This is the commutative law. So all the n number of input gate you have, like and or your or, they will follow this commutative law, right? Associative law, we all know associative law. Distributive law, this is very important, right? If it is a plus bc, then first you will write b with a, like a plus b, then you will write a with c. So here you can say this expression is in SOP form. Now this expression is in POS form, product of sums, right? Similarly, absorption, a into a plus b, you can write it like this, na, a plus ab, then you will take a common, so it is like this, a plus ab, right? So when you will take a common, here we have 1 plus b, right? 1 plus something is always going to be 1 only. See, this is the logic or operation we are performing here, right? Similarly, De Morgan's theorem, student, very very important. Most of the time you will take the help of this law to simplify the expression. So how you will remember it? If it is ab bar, this is whole term bar na, so you will write down the first, you will write down the both the terms a and b. Here we have only variables, so a and b, then you whole bar will become individuals bar, and this and sign will be replaced with or, right? Like this you can solve it. So now let's discuss the OR form. So 0 plus something is going to be something only. So here we have a. 1 plus something is going to be 1 only. A plus a is going to be a. A plus a bar is going to be y1, because if the value of a is 0, then a bar will be 1. So out of these two terms, every time you will have 1 plus 0, right? A plus b can be written as b plus a. Similarly, this is the associative theorem. Here you it is the simple multiplication, right? And here this thing is already explained. And this whole bar will become individual terms bar, and plus will be replaced with the dot sign here, right? It is the AND operation. Next one. So these are the few logic gates. I know you all are aware of these gates, right? AND gate, OR gate, right? Not gate. So students, I will provide this PDF to you, or this talk to you, right? So you can quickly revise all these things, right? See, these things are very important. I know everybody know that, okay, a into and gate is going to be a into b only, but these things are equally important. How you will enable this gate? The enable make see, enable means, see, if you have connected 0 here, if this terminal is grounded, so the output will always be 0. So the second input will not be there, right? The second input is not important in this case, right? So this is known as the disabling this input. Now enable, so see, if you are connecting this input to high, or the logic 1, then what will happen? Output is going to be 1 into this a. Now the output is decided by this input, so which means that your this circuit is now enabled, right? Now both will follow the commutative and associative. See, both are following commutative law and associative law. That's why we can use the 3 input AND gate, or we can use the 4 input AND gate, like this. Okay, so similarly here, right? Not gate, we all know what is not gate, right? XOR gate. So students, sometimes if as I told you in dual, if you have to find out the dual, you have to follow the 3 steps, right? Suppose if you have to find the complement of any this thing, then what you will do? Or will be replaced with and, right? And your this thing 0 will be replaced by 1, and you will, if a will be replaced by a bar, if you have a bar, then a bar will be replaced with a bar bar, so it is going to be a only, right? And if you will draw the circuit, see, this is the circuit, this is a logic gate, right? If you have to find the dual of this, then what you will do? You will put bubbles here. See, here we have 3 terminals, so put 3 bubbles like this. So the meaning of bubble is nothing but inverter only, right? So if this is a, this is b, then output is going to be, here we have bubble, so this is going to be a bar, this is going to be b bar, and NAND operation we have to perform, then whole bar, like this. Okay, now let's simplify it. So it is going to be a plus b bar bar, so this is equals to a plus b only. So here you can see, and the dual of and is or only, right? So it is correct. Now if you have to find out the complement, if this is the and gate, then how we will find the complement? We will put one bubble at the output terminal. So if this is ab, this is ab, then output is going to be ab bar. So ab bar is the complement of ab, and a plus b is the dual of ab. Okay, like this you can remember it. Now XOR gate is very important, students, right? So if you will see the truth table of XOR gate, so output is going to be 1 if you have odd number of ones. So here we have 2 zeros, so 0. Odd 1, so 1. Odd 1, 1. Even 1, so 0, like this. And what is the XOR table? So it is going to be your output is going to be high. See, first of thing, XOR is nothing but it is just a complement of the XOR. So you can directly fill the table like this. But if you will see here, your output XOR gate output will be high when both the inputs are equal. Okay, and if you will discuss the 3 input, then what will happen? Similarly, XOR for odd number of ones, you will write output as 1, and rest of the cases you will write 0. Okay, so now let's discuss these laws here. See few important points here. So output, okay, this is already it follows commutative law, associative law. And student, one more thing, we will always have 2 input XOR and XNOR gate. We will never have 3 input XOR or XNOR gate, right? This thing is very important, keep this thing in mind. Okay, it follows commutative, associative only for 2 inputs, right? A XOR B is going to be 0. So how you will perform A XOR? So what is the Boolean expression for XOR gate? So this is going to be A bar B plus A B bar, right? So here we have 0. So suppose B is 0, then this term will be 0, and it is a, so a into 1 is going to be a, so a XOR 0 is going to be a. Similarly you can find this thing. Okay, don't get confused. If you feel difficult to remember it, then just remember this Boolean expression, and accordingly you will find the answer. Okay, here you can see a XOR a XOR a XOR n number of times, right? So if the value of a is odd, if the value of n is odd, so here you can see if you have n, suppose 3, right? So a XOR a is going to be 0, and 0 XOR a is going to be a. So if you have n your odd number, then answer will be 0 a, sorry. And if you have even numbers of n, if the value of n is even, then output is going to be 0. Here you can see this. Okay, like this you can find out the answer. Now this thing a XOR a b bar, whole bar, right? So let's find it out. See why I'm discussing this thing here. So this, in the, see, you can, one question will definitely there from, will be there from this topic. Okay, from the Boolean algebra, they can ask you to simplify the expression, they can ask you to write down the Boolean expression for the given circuit, or you have to draw a circuit from the given Boolean expression, right? And sometimes they can also ask you for find the minimum number of NAND gate required, right? So we, okay, I will discuss this thing. Let me first cover it. Okay, so how you will do it? So suppose this is a only. Now let's assume this is the c variable here. So a XOR c, right? Now write down the expression. So this is going to be a bar c plus a c bar, right? Now what is the value of this c? C is ab bar, right? So at the place of c I will write a bar and this ab whole bar plus a into ab bar bar. So bar bar got cancelled, right? So this is going to be a bar into ab. So this expression is going to be 0. Now let's solve it. So this is a bar. Now ab whole bar can be written as a bar plus b bar, right? I can write it like this. Now multiply here. So this is going to be a bar plus a bar b bar, right? Now let's take a common. It is complete bar na, ab bar. Okay, here we have a, so a bar b c bar, so a bar bar got cancelled, so here we have a b. Oh sorry students, here we have a, that's why we are getting this thing. Okay, sorry, this is a. Okay, this is a, this is not 0. So let's multiply. So this is going to be a into ab, right? So this is going to be ab only, right? The second term is ab. Now let's find out first term. So a bar into this bar, whole bar can be written as the individual terms bar, then plus. Now multiply it. So this is going to be a bar plus a bar b bar. Now take a bar common. So this is going to be a bar only, right? This is a bar only now. Now let's write here a bar plus ab, right? Now first I will write a bar plus a, then I will write a bar plus b. So this will be 1, so answer will be a bar plus b. Here it is a plus b again, I think a plus whole bar. So this is going to be c, a bar c, a c bar. So it is correct only, right? So it is ab only, it's a bar c, a b bar whole bar. I can write it like this, a b bar whole bar can be written as a bar plus b bar multiplied by a bar. So it is going to be a bar plus a bar b bar. Now take a bar common. So it's 1 plus b bar. So this is going to be 1. So it is a bar plus ab. Okay, so students, the answer is this only, a bar plus b. Okay, there is a mistake. It is going to be a bar plus b. Okay. So you have to remember just this formula only. Rest is just calculation. Okay. NAND gate. Next is NAND gate. AB whole bar. Okay. they follow commutative law, but it will not follow associative law. So if it is not following associative law, which means that we can't use three input NAND gate, right? Because to check associative law, we want three variables, na. So if it is not following, which means that we can't use three input NAND gate, we always use two input NAND gate. Similarly, NOR gate, NOR will never follow associative law, so we always have two input NOR gates only. Three input NOR gate will not be there until and unless it is not mentioned in the question, right? All right. So next, XNOR gate. So similarly, what is the expression for XNOR gate? It is going to be AB plus A bar B bar. See, for the two input XOR gate, you can easily write down the table. Now, how you will write the, you will fill the table for this thing. Okay, if you will have your this thing. See, oh, you have to remember all these things like this. Okay, see, if you don't remember it like this, then you will write down first the table for XOR gate, then just 0 will be replaced by 1 and 1 will be replaced by 0 in the table of XNOR gate. Okay, like this you can see. This is again very simple. I already explained for XOR, so you can, I hope you can do it. Now here you can see a table is given XOR or XNOR gate. Output is 1 for odd number of ones. Output is 1 for even number of ones in the input signal. Okay. Odd number of ones detector. So yeah, if in any input sequence, if we have odd number of ones, then output will be high, right? If output is 0, which means that in the given sequence the number of ones are even, right? So similarly it can be used for the even numbers. It is inequality detector. This is equality, because when both the inputs are 0, output is going to be high, right? Anti coincidence, coincidence. So these are the names of this XOR and XNOR. These are the symbols, right? Okay, this means this bar, this is this bar. Okay, right? And students, one more thing here, here we have bar. Okay, here we have bar because XOR is A XOR B will be equals to A XOR B complement. This relation is very important. See, A plus B, okay, A plus B bar, this is your OR gates Boolean expression, this is the NOR gate. If you will take the complement of this thing, so this will provide you the OR gate, right? Similarly, this is the expression for XOR, this is the expression for XNOR. If you will take the complement, you will get this expression. And similarly, if you have to find A XNOR B, then this is going to be equals to A XOR B bar. Okay, these two relationships are very important. Okay, I hope this is clear to you all. Next, K map. See, K map is really very important. Okay, so students, uh, let me explain you something. See, if you will write down the Boolean expression from the truth table, okay, then the Boolean expression will contains, or the Boolean expression will be in its standard form or canonical form. Both means same. Okay, and if you will get your Boolean expression from the K map, then that expression is going to be in its simplified form. Now we have, see, one more thing, NAND and NOR are the two universal logic gates. You can implement any circuit using these two NAND gates, these two gates, right? Similarly, MUX is your universal circuit. You can implement any logic gate, any circuit using the MUX, right? So if in the problem it is given that you have to implement the given expression using the logic gates, then you will write down the Boolean expression in its simplified form, then you will implement the circuit. Okay, now if it is given that you have to find out, you have to implement the circuit using MUX, then you will use the standard form, or you will use the canonical form to implement the circuit using MUX or decoder. Okay, I hope this is clear to you all. Okay, this is a very important thing here. Okay, now K-map. See, using the K-map, again you can write down the Boolean expression in SOP form and POS form, right? So in the K-map, these are the few steps that we have to follow. Okay, first of all, we will fill the table. Okay, from we will fill this thing for from the given truth table. Okay, then we will combine the ones. So we will try to form octet, quad, pair, and last one is cell only, right? If you are able to make a group of 8 ones, then that will be known as the octet. And see, if you have okay, I will discuss this thing next. Okay, wait. So and each you will see you can directly fill the table from the truth table, or if your boolean expression is given in the terms of mean terms and max term like summation small m 1 2 4 7, then you can directly fill this data here and you will get the boolean expression, right? Okay, in sop form we will combine the number of ones, and in pos form we will combine the cells, okay, having 0 as the this thing. Okay, so now implicants. Each minterm in the canonical expression is known as the implicant. Okay, what is prime implicant? It is the product term obtained by combining maximum possible cells in the K-map. Okay, while doing so, make sure that the smaller group is not completely inside the bigger group. Okay, that will be known as the prime and student, one more thing, the boolean expression that you will get from the k map, it is not necessary that you will have the same this your the this thing only one expression. You can have more than one number of expression if you are solving your problem using the k map, but it is the thing that expression is going to be in its simplified form. You will not require to further simplify that expression. Okay, that is the good thing about the k-map. Now essential prime implicant. So essential prime implicant will always be less than equals to p. So if this is the prime implicant, then essential prime implicant will be like this is the Venn diagram. So a prime implicant is an EPI if and only if it contains at least one mean term which is not covered by other multiple groups. So there is only one way to get that mean term. Okay. So now these are the few important points. Okay. So if you are combining 8 cells, then you will get one octet and you will remove the 3 variables. If you have 4 variable problem, then out of 4, 3 will be eliminated if you are combining 8 cells. If you are combining 4 cells or if you are forming quad, then 2 variables will be eliminated. And if you will consider one cell only, then one variable will be eliminated. Two cells, na? So the meaning of two cells is pair. So one will be eliminated, right? So let's first discuss the SOP form. If we have two variables, right, then K-map representation will be like this: A0101, right? So in POS form, this is not going to be, in SOP form, this is not going to be AB. This is going to be A bar, B bar. Okay, here we have A bar, B bar. A bar, B bar, sorry. This is going to be A bar, B. This is in POS form. It is incorrect. Okay, it is incorrect. I'm considering POS form now, so this is incorrect. Right? It is going to be something like this. A, B, we have two variables, 0, 1, right? So this is going to be A bar, B bar. This is going to be A bar, B. This is going to be A, B bar, and this is going to be A, B, right? So if all the ones are there, then output is going to be, X is going to be 1 only, right? And if you have two ones like this, remaining two are 0, then you will make a pair like this, and expression output is going to be B bar. A will be eliminated, right? This is the K map for three variable, right? Here you can see number of blocks are 8, 0, 1, 2, 3, 2, 4, 5, 6, 7. This thing is very important. 0, 0, 0, 1, 1, 1, then 1, 0. See, at a time only one bit can change, right? If you will directly write after 0, 1, you will write 1, 0, then both the bits are changing, right? So I will write 1, 1 here, then I will write 1, 0 here. Okay, so this is going to be A bar, B bar, C bar, and this last one is going to be A, B, C bar. Okay, and if mean terms are given like this 1, 2, 4, 7, then you can directly write here 1 here. Here we have 2, so 1 here, 4. So I will write 4 here, 7. So I will write 1 here. Now here you can see you cannot combine any cells, so 4 terms will be there in the output. Okay, so number of PI is going to be 4 and EPI is going to be 4. Okay, these are the zeros. Okay, here you can see this is an example ABC. You will see if in the truth table, if this is the order in which you are writing inputs, the same in the same order you will write here. Okay, so 1 1 you will combine these two ones. So this is going to be a PI, EPI. Why? Because this is the only one way to combine this one. So this is going to be EPI. Similarly, this is going to be EPI. Now, if you are combining these two ones like this is the unnecessary word, this thing. Okay, because these two ones are already covered, so no need to write this. So if you are writing it like this, so expression is going to be A bar plus A plus, no, here we have this thing also, no, C, and here we have B. Right? If you will write it like this, then this is going to be BC. So this BC can be eliminated. Okay, there is no role of this BC. Functionality will not change. So one AND gate is removed. No need of implementing this expression. Okay, like this. This is a 4 variable problem. Okay, 0 0 0 1 1 1 1 0 like this. Okay. So here you can see we have to write in SOP form. So we will combine the ones 0, 1, 3. Okay. So we have to combine the ones like this. So this one adjacent to this one, there is no one. Yeah, here we have one. So I will make a pair like this. Okay. Now here we have two ones, two ones. So I will make a quad like this. Okay. Now we are left with these two ones. So I will make a pair of these two ones. So total 1, 2, 3. 1, 2, 3 terms will be there in the Boolean expression. So if we have quad, so two variables will be eliminated. So this is going to be here. Which one is constant? A is constant, so A bar. And here C, D is constant, so D bar plus. Pair, so only one variable will be removed. So A, B, C plus. For this, it is going to be B bar, C bar, D. So these are the three terms here. 4 add group we will get A, B. See, this is for POS form, okay? It is in, if we will consider the logic 0. Okay, this is incorrect, okay? Don't consider these few lines. It is incorrect. Okay? Right, now the second is POS. And see students, I will quickly show you the how you can make a quad, and for 4 variable problems, good questions can be formed, right? See, if you have ones like this, so you can make an octet like this. So answer will carry only one variable. Similarly, if this one you can make a pair like this, and for these two you can make a quad like this. Okay, so total three terms will be there in the output. Like this you can write down. In POS form you will fill the k map with zeros. This is correct this time. This is correct. Okay, this is correct for three variable, right? So here you can see this is the expression. See here pi will be given to you. Here it is again incorrect. Pi will be given to you because in POS form we will consider the max terms. I will make changes in the final document, okay, and I will provide the link for the document. So from there you can follow this thing, okay. So pi m for the max term. So 0367. So 030367. So I will make a, now I will combine the zeros here. So here you can see I'm combining these two, I'm making a pair. So here the value of a is 1, so I will write a bar plus the value of which one is constant, b. So value is 1, so I will write b bar into this one. A is changing, this value is same, so this is going to be b bar plus c bar. Similarly here we have 0, so there is no way to combine this 0. So we have this, it will contain all the three variable a plus b plus c. 0 0 na, so I will write like this. So this is the answer. Okay, this is the answer, right? It is in POS form. Okay, students. So here you can see in all the examples don't care is not there, right? But in KMAP, if don't care is given to you, then it's your choice. If taking the help of don't care, if you are managed to get octet or quad, then you can consider that x. The meaning of don't care is that you can consider x as a 0 or you can consider x as a 1. It's user's choice only, right? Similarly, in the case of POS, these are the max terms. You can write it like this. Okay, again a mistake, pi capital M will be there. Okay, now this time it is correct. So you will have four terms here. Okay, it will be like this. Now multiply to get this in its POS. One question will definitely, if it is from the K map, or it can be asked from the your this thing. You see, two types of questions can be framed. One from the K map, okay, the problem in which you have to take the help of K map to solve the given problem, right? And some circuit may be given to you and you have to write down the Boolean expression, okay. And if you have to write down the Boolean expression, so information may be given in this form, okay. So you must know all these forms, right? So this is one question will definitely from going to be from this topic, and this topic is again very easy, okay. So you can at least secure this, the one, it can be asked for one or two depending upon the this thing. Okay, next one is combinational circuits. So see students, any Boolean expression you are implementing, that is going to be a combinational circuit only. The circuit in which there is no memory element, there is no memory element, there is no clock signal, okay, that will be known as the combinational circuit. Any Boolean expression is given to you and you are implementing some circuit, so that is going to be combinational circuit only. See, the circuit in which the output is not given back to the input side or there is no feedback, that circuit will known as the combinational circuit, okay. So here are the few yeah, this thing important combinational circuits are here. We have half adder, right? Full adder, half subtractor, full subtractor, right? Multiplexer and comparator, decoder, encoder. These all are the combinational circuits only, right? Multiplier, right? So just you have to do for the given your this thing circuit, you will fill the truth table, okay. So this is a half adder, so you will perform the operation, addition operation, both the inputs, accordingly you will get the sum and carry. And now from the given this table you will get the Boolean expression, and the expression is going to be something like this: a XOR b for sum, a b for carry. Now you can implement, if you are using only NAND gate to implement this adder, then you will need 5 number of NAND gates. If you are using only NOR gates, then you need 5 number of NOR gates to implement this half adder circuit. Okay, and one adder will always add one your the two your bits. Okay, it will perform the addition operations only single bit input data. Okay, audio video perfect, good. Okay, so see here, this is the expression. Next one is the full adder. In full adder you have to add carry also, right? Because see, if you are adding 3-bit data like this, right, so you can have carry from the previous stage na. So that's why we will use full adder, right? For the addition of these 2 bits you can use one half adder, but to perform the addition on these bits you need full adder, so that you can have one carry from the previous stage also na. So you have to consider that also. So this is the logical expression for sum, this is the logical expression for carry, right? So why we are using this expression, if you will write in the terms of mean terms, so this is going to be 1 2 4 7 like this. Okay, you can write it like this also. Okay, now why we are writing in this order, because see, A XOR B you will get from here, right? If you will implement this circuit, I will explain this thing in the look ahead carry adder. So if you will see, if you will write your expression in this term, then the output of this can be directly used here in the calculation of carry, right? Now to implement this expression, you need 9 number of NAND gates and 9 number of NOR gates, right? This is the truth table for carry and sum. Now this is the circuit here. Okay, this is A XOR B. As I told you, we can use only 2 input XOR and XNOR gates. So here we have the carry from the previous stage, so sum is going to be A XOR B XOR C, right? Similarly, this is going to be C, and this is going to be A XOR B. So output is going to be C into A XOR B, and this is AB, so this is going to be AB. Now addition, so this is going to be C out. Okay, and how you will implement a half full adder using half adder? So this is the half adder circuit, right? And this is again a half adder circuit. So this input is given as the carry, and this output will sum. We will again perform the sum operation on this. So this is going to be A plus B. Okay, it is arithmetic operation, not logical. And this is sum is going to be, this is A XOR B. Now this is going to be A XOR B XOR C. Right here, this is nothing but C in, and this C into A XOR B. This is C out, right? And this is AB, right? So perform addition operation. So this is going to be carry, right? Like this you can do it. Now see, n bit parallel adder. So if you are performing the addition operation on n number of bits, right? If you have 2 inputs A and B, so input A will have n number of binary and n number of bits like 1010 like this. Okay, so the worst case delay is nothing but, let's calculate. See, first you will add these 2 bits, the LSB ones, right? And the sum. Now the carry of this stage will be given to the next stage, because carry will travel now. So similarly carry will travel like this. This is the C out. So to get C out, delay 1, delay 2, delay 3, delay 4 and delay 5, right? 5 number of this thing will be there. No, sorry, we will not consider this one. This is the addition. So delay 1, delay 2, delay 3, delay 4, right? So after 4 TPD, right, or after n minus 1 TPD, carry will be available. This carry C in will be available, right? So after the arrival of this cn, then only addition will be performed, right? So the worst case delay is written as n minus tpd carry, because the time taken by this carry, or the carry will be available after the n minus 1 tpd delay, plus maximum sum plus carry. Now this adder will perform the addition operation and it will generate the carry. So this is the delay provided by this last adder. Okay, so this is the worst delay. So when I will design the adder, look ahead carry adder, so this delay will be less, because this is the critical path delay. If somehow I manage to reduce this delay, or if this cn is available uh, soon, then this delay will be reduced, right? Next one is subtractor a minus b, right? So here I'm performing a minus b operation, right? So the borrow is a bar b. If it is b minus a, then borrow expression will be b bar a. This thing is important, okay? So you can revise it. This thing, expression is going to be XOR b. This is going to be a b bar, and NAND gets 5, NOR get 5, like this. Similarly, this is the expression for the half subtractor. See, the difference and some expression is going to be same only, a xor b xor c. The thing that will change in both the cases, borrow expression and carry expression will change only, right? Difference and sum will never change. Okay, see here, this is a 3-bit subtractor, full subtractor. So what is the expression? ab bar, okay, ab bar plus a xor b bar c. Okay, this is the expression for carry. For, sorry, for borrow, here it should be borrow, it should be difference here, it should be borrow. Okay, these are the just this thing, okay. Um, Ignore it. Okay, now we will fill the table, and from the table we take the help of k map and we will get the expression for difference. Okay, similarly for the borrow, this is the circuit for full subtractor. Okay, this is the circuit full subtractor made up of half subtractor. Next one is look ahead carry adder. This is very important. Okay, this is the fastest one. Okay, adders have maximum complexity. Obviously, complexity will be different because we are separately generating carry now. Okay, so n number of XOR gate required, n number of AND gates required. Now, first I will show you the expression. So this is ABC, 3 inputs, carry. Okay, so 0 when no need to generate carry. If it is like this 1 0 1, here we have carry, so carry will propagate. Now we will generate carry here. Okay, now see here, as I told you in full adder, the output of first XOR gate is this pi. Okay, and gi is nothing but the carry expression. See, if you will consider half adder, then this is the expression for sum, this is the expression for carry, right? Now I will take the help of these things. Gi means generate, carry generate. Pi means carry propagate. Okay. Now sum is nothing but pi into c only, na? So it is nothing but a XOR b XOR c. Okay, I will write I here. Now what is carry? Next is carry is going to be gi, that is your ab, plus pi ci. So what is the value of pi? A XOR b c, right? This is the expression for carry, na? So I'm using the same expression here. Okay, now see here, ci c1, this is the output of first adder, right? Carry output, that is on the right hand side, the extreme right one, right? So this is going to be g naught p naught plus c in, right? So this is going to be a naught b naught plus a naught XOR b naught into c1 c naught, sorry, right? Similarly, C2 is nothing but G1 into P1 C1. So the value of C1 is this, right? So at the place of C1, I will put this value. And P1 is nothing but A1 XOR B1, right? So like this, you will write down the for this thing. Now I will separately generate the carry because at level 1, you will be ready with P0, G0, P1, G1, P2, G2 like this at level 1. At the second level, you will generate the carry. Okay, this expression. Inside this level 1, that inside this level 2, we will have these circuits for these ones. Okay, see if this is P0. P0 is not there na, in this circuit. Okay, G1, G2, G3 consider. So P0 is not there. Okay. Okay, I will remove this diagram and I will add the proper one, right? This is incorrect. I think C note, G note is not given here, right? So I will explain you here, don't worry. So at level 1, this is the level 2 and this is the level 3. At level 1, we will generate the P naught, C naught. Okay. Then in the level 2, we will generate the value of C1. Okay, we will generate the C1. Then we will, for C2, we will draw this circuit diagram. For C3, we will draw this complete circuit diagram like this. Now, by looking at this expression, if we have 4 bits, right, then you can find out the number of gates required here. See here. For P0, we need 1 XOR gate, 2 XOR gate, 3 XOR gate, 4 XOR gate required. Right? For some expression, you will again require 4 XOR gates. Because you have to perform XOR operation on this thing also now, on some. See at level 1, n number of XOR gate, n number of AND gate. And this is for some. And this is for the carry, that is your AB, right? A naught, B naught, A1, B1. So this is nothing but GI only, na? So this is for GI and this is for PI. Okay, now the second level. This is the level inside this. We have two levels, level 2 and level 3. Level 2 and level 3. Okay, level 2, level 3. Why level 2, level 3? Because we need AND gates and we need OR gate. So to perform AND operation, we call it as a level 2, and for addition, we will call it as the level 3. Okay, so here you will see n into n plus 1 by 2 number of AND gates and n number of OR gates. So why n number of? Because see, we are getting 4 carry values, so 4 OR gates required. Right? Now AND, one AND gate here, 2, no sorry, here in this expression 1, here we need 1, 2, 2, 3, 4, 5, 6, 7, 8, 9. So 9 number of gates required here. And if you will take 2 input, then again here at this step you will need 3. At this step you will need 3 and here you will need 3. No, here you will need 2. Yes, here you need 2. Here you will need 2. Here you will need 3 like this. Okay, here you will need 1, then 2, then 3. 1, 2, then 3. No, here you will need 4. Here you will need 4. Here you will need 2. Here you will need 1 like this. You can calculate, okay? In the document, I will provide the accurate circuit, okay? It is not the right one here. It's right only, but let's see here how you will understand. How many gates are there? 3? 3, 6. and number of inputs are 3 only, right? So 3 into 4 divided by 2. So this is going to be 6 only, right? This is the level 2 circuit. It is correct only, but it is for the level 2 and level 3. This is the level 2 and this is the level 3. This is, so here level 1 is not here. This is the level 1. Okay, level 2, level 3. Then at the end we will have level 4. So we will use these carries to find out the value of sum. So this is, see, this is correct only, but it is not a complete circuit. Okay, so this is for the level 2 and this is for the level 3. Okay, now multiplexer. So it is also known as the data selector. Okay, 2 raised to power n to 1. If we have n number of select line, then 2 raised to power n number of data lines can be connected. So depending upon the number of data lines, you will choose the select line. Okay, this is a 2 to 1 mux. Okay, so if s is 0, then I naught will be passed to the output. If s is 1, sorry, s naught is 1, then I1 will be passed. Okay, so here we are not performing any operation on the input data. We are just selecting the data and we are providing to the output terminal. Okay, so here we are not performing any operation. See, this is the Boolean expression for mux. S naught bar 0 will be selected, S naught 1 will be selected. Okay, and this is the circuit diagram here. Okay, this is a 4 cross 1 mux. So 4 number of inputs, so 2 number of select line will be used. So 2 select lines will provide you the 4 possible combinations. So 4, and we are available with the 4 data lines, right? For this input combination, I naught will be selected, right? So this is the final expression for 4 to 1 mux. This is the circuit diagram for 4 to 1 mux. Okay, now in the examiner can ask you to design 16 to 1 mux using 4 to 1. Now see here 16 number of data lines are given and we have only 4 to 1 mux available with us. So to get for 16 number of data lines, let's divide it. So 4 number of mux will be required at the input side. 4 to 1 mux, right? So if we have 4 to 1 mux, 4 mux, such 4 mux we have, so 4 number of outputs will be available with us, right? So I will use one more 4 to 1 mux to get the output. And student, at this level you can use the same select lines here. Okay, you can use the same select line, but these two select lines should be different from these select lines. Okay, here you can't take s1 s naught, right? These select line can be same because at a time we are selecting only one only na. So that's why you can keep the same select lines here. Okay, now these are the implementation. If you will implement these logic gates using mux, so these number of mux will be required. Okay, if you are designing half adder using mux, then 3 mux will be required. If you are designing this thing full subtractor, then 2 will be required, right? Now demux is nothing but it is just opposite of the mux. So it is one to many output, right? So it is also act as a data distributed, right? It will be something like this: input, these are the outputs, y0, y1, this is the s. Okay, now as I told you, with the help of mux is a universal circuit, so we can implement any circuit, right? So, and I told you to implement the circuit using mux, your this thing Boolean expression should be in its canonical form, right? So suppose if we have three variables and we have to use 4 to 1 mux only, then you can implement the two variable problems very easily. But to implement the three variable function, you will need one NOT gate, or you may need AND gate, OR gate, right? Some extra gates will be required. So 4 to 1 mux can easily implement the circuit for two variable inputs. Okay, and if you want to implement 4 to 1 mux using and if you are available with one NOT gate, then you can implement the all three variable input. If you have three variables problem, then you can implement the function. Similarly for 8 to 1, so this is 2 raised to power n cross 1 na? So you can implement all the three variable functions, but not all four variable functions, right? So students, suppose this is a 4 to 1 marks, okay, and you have 8 variable problems, 3 variable inputs, 3 inputs are there in the variable, so you can use only 2 select lines, right? Here we have 4 such. So what will happen, suppose these are the 3 variables, so you can use AB as a select line, you can use BC as the select line, or you can use CA as a select line. So at these 4 input data lines, you can use, if C AB are using here, then C bar 0 and 1, these are the 4 possible data values here, okay. Like this you can implement. And if you have 8 to 1 marks, then what will happen, all the 3 inputs variable will be used as a select line, and the 8 data lines will be connected to 0 or 1, okay, and you will get the output. Similarly, oh sorry, let's discuss the decoder. Decoder we use to convert the binary into the other coded signals, right? You will code the binary into other code, like it can be octal, it can be hexa, or it can be like this thing only, okay. So this is the basic diagram for this thing. N to 2 raised to power n decoder, here we have n number of inputs, then 2 raised to power n number of outputs will be possible, okay. This is the truth table for the decoder, as its name said, decoder. So these are the 4 possible input combination. Output, out of 4 output, only one will be high at a time, okay. Q naught is high, right? Generally we write in this order, okay. This is LSP, this is MSP, okay. For this input combination, Q naught will be high. For this input combination, Q1 will be high, like this you can decode your this thing, okay. Now this is the circuit here for decoder. Now encoder will encodes the, sorry, it is opposite here, okay. Let me see. Okay, the circuit diagram of encoder is 2 raised to power n to n, okay. 2 raised to power n to n. So the value of n is 2, then this is going to be 4 to 2 encoder, okay. So binary weighted encoder assign codes based on the input position using the binaries, okay. So now this is it, it's very easy, you can, I think you can do it on your own, this thing. This is the table, if these are the inputs, then this is going to be the output. Encoder and decoder are just uh, uh, opposite, right? Okay. If this is the input of decoder, then this will be the output of the decoder, and if this is the input of encoder, then this is going to be the output of the encoder, like this, okay. So here we have only OR gate, okay. Now this is the 8 to 3 encoder, 8 inputs, 3 outputs here, right? Like this you can fill the table, okay. So in the inputs of the encoder, only one will bit be high out of the 8 bits, okay. So we need only OR gates in the implementation of encoder, okay. Now the priority encoder, this is important, okay. So 4 to 2 priority encoder has the 4 inputs, these are the 4 inputs, so 2 outputs are there, A0 and A1, right? And Y3 has the highest priority, this is the MSB, it has highest priority, it is given in the this thing. Y0 has the lowest priority, okay. Why we are using this thing, if we have more than ones in the input, then to which input you will give the priority, right? See here, if all the bits are 0, output will be 0, these two will not matter here, right? Similarly, see here, if this bit is 1, then output is 1. Now if this bit is 1, we will not bother about the this bit, because this is the least significant bit compared to this one. So output will, we will provide the output by looking at this input. Now if this bit is 1, so axis don't care if it can be like this, it can be like this, it can be like this, right? So we will give the priority to this y2. Okay, these two will be act as the don't care, so this will be the output. Similarly, if this MSB is high, then we will not check the remaining 3 bits. We will provide the output. This is known as the priority encoder. It is important. Okay, priority encoder is important. Now this is the expression for using K-map only. Now next one is the sequential circuit. Sequential circuit again is a very important topic. Okay, so it is nothing but combination of the combinational circuit and memory input, and output is given back to the input. So the output of this system sequential circuit will depend upon the previous values of the output or the previous stage, right? So what is the basic memory element here? We have latches and flip-flops, right? So this is a NAND latch, this is a NOR latch. Here you can see output is given back to the input of this gate, and output of this gate is given back to the this. And in case of sequential circuit, we have two outputs and they are opposite. If this is Q, then this will be Q bar, right? So out both the this thing output available in its complement form and its true form, right? If this is 0, then this will be 1. If this is 1, then this will be 0, right? So it is available in the this thing. Now see here, this is a NAND latch. Okay, now let's fill the table. How you will fill it? Why I'm writing plus? These are the present state and these are going to be next stage. Suppose if the value of a is 0, b is 1, this is 0, so x is definitely going to be 1. Now here we have 1, 1 into 1 is going to be 0, so it will be remain like this 1 0 for this input combination. If this is 1, this is 0, then what will happen? Here we have 0, here we have 1, so 0, so this is going to be 1, and here we have 1 1, so this is going to be 0, so it will be like 0 1. If both the inputs are high, then previous stage will decide the output, because this is 1, this is 1. So second output will decide the second input will decide the output. If this value is 1, then 1 into 1 is going to be 0, 0 into 1 1. If here we have 0, then 0 into 1 is going to be 1. So it will, for this input combination, your this thing will be in the memory state or in its hold state, because it is holding the previous value of the output only, right? Now if both the inputs are 0, then what will happen? Output will be 1 1, which is an invalid state, you can see here. This is invalid. The rest you can understand, right? Okay. SR NAND latch, SR NOR latch. We are implementing the latch using NAND and NOR. Okay. Now flip-flop. If you will use the clock signal for the synchronization, then we call it as a flip-flop. Latch plus clock is equals to flip-flop. Latches are universally not unique and hence their truth table are not unique. Flip-flops are universally unique, so their truth table are also unique. So now I will discuss the flip-flops here. SR flip-flop. First one is SR flip-flop. Okay. Preset. If this is active high pin, if this is 1, then output will be 1 0. Okay. If it is 0, then these inputs will decide the output state. If clear is 0, then these inputs will decide the output. If clear is 1, then output will be 0 1. It will clear the QN. Okay. Now this is the circuit diagram of a SR flip-flop. Here you are applying clock as the input of these two NAND gates. Then this output will be given as this stage. This is a latch and this is for the plus this circuitry will be give you as a flip-flop. Here is it, here you can see if S is 0, R is 0, S is 0, R is 0. Output will be decided by the previous state. So it is in its hold state, or you can call it as a memory. If S is 0, S is 0, R is 1, R is 1. So This is Qn, right? 0 and 1, but Qn plus will always be 0. So this is your reset state. Here this is 1, this is 0. Output is high for both the Qn value. So this will be as known as the set. 1 1 invalid. Right? Like, see, this is the characteristic equation for SR. R bar will not be there. It is going to be S plus R bar Qn. Okay, this R bar is not there. This is the characteristic equation. Okay, this is a JK flip flop. Okay, this is the circuit of JK flip flop. This is the truth table. 400, it will be in its memory state or hold state. 40101, it is set, reset, sorry. This is set and this is the toggle. See, this is the disadvantage of SR. Now we have an invalid state for these two, for this input combination. So this is eliminated in JK flip flop. When both the inputs are high, output will toggle. Okay, if the previous output was 0, then present will be 1. If present is 1, then next is going to be 0, like this. This is the characteristic equation for JK flip flop. These characteristics are equations are very important. J bar Qn plus K bar Q1. Here you can see, if you will compare the characteristic equation of SR flip flop and JK, then S is going to be J bar Q1. Okay, D flip flop. Whatever input you will provide here, it will pass to the output stage. So the easiest one, right? This is the this thing circuit of D flip flop, and this is the characteristic equation of the D flip flop. T flip flop. If the value of T is 1, then output will continuously toggle. It will go like this. If T is 0, then it is going to be in its hold state. Okay, so this is the expression for this thing. Qn plus 1 is nothing but Qn XOR T. Okay, now race around creation. This is basically occur in the level triggering. Okay, this is the case when your input is not changing. See, this is the clock signal. So your latch is transparent for this thing, right? Okay, flip flop is transparent for this duration. This is the width of the width of the your pulse, right? So your input is not changing, right? Input is constant, but output is given back to the input. So output, because of the output will continuously toggle, right? Right. So that's why, to remove this race around the conditions, you have to implement the master slave flip flop, or you can do it like this also. If the TPD, the propagation delay of the flip flop, is greater than TPDW, right, then race this thing will not be there, right? You can omit this thing, right? And this TPD should be less than the time period of the clock signal. If this condition is you are able to meet, then there will be no race around condition in the flip flop. Okay, this is because of this should be there, right? But TPD is less than TPW, that's why we are having this problem. Okay, so you can use S triggered flip flop, or you can meet this condition, or you can use a master slave flip flop. These are the three remedies for this thing. Right, now next one is the conversion of the flip flop. So students, what you have to do, suppose you have to convert, you have to implement SR using D flip flop. Then what you will do, you will write down the excitation table for the, sorry, you will write down the characteristic equation. You will fill the characteristics table for the SR flip flop, and you will fill the excitation table for the D flip flop. Okay, so see here, present state, next stage, SR, JK, D, T, right? So here you are implementing the D flip flop using SR, D flip-flop using JK, T flip-flop using SR, T flip-flop using JK. So here you 0 1 0. So this is nothing but the characters excitation table. And these are the characteristics table, right? This is also excitation table, right? Now you can write down the D in the terms of Q, Qn plus SR and JK, right? Now you let's take an example. Okay, we are converting SR to JK, right? So JK, I will write down the characteristics table for the JK flip-flop, right? Then Qn plus, then I will write down the excitation table for the SR. Now with the help of K-map, I will fill these cells and I will get the expression for S in the terms of these for this thing. Okay, similarly for the R. Here you can see S is equals to JQN bar, R is equals to KQN. So here you can see this is SR latch, SR flip flop. So this S is nothing but J into QN bar, and this R is nothing but K into this Q, right? This is it. It's very easy. Just you must remember this thing only. Okay. Similarly, you can do this thing. Now, next one is the counters. So this is one of the application of the flip flops, right? So in the counters, we will get counters using the cascading of the flip flops, right? So we use the counters to count the number of pulses, and they can also be used as a frequency divider circuit. Okay, or the waveform generator like this. So the number of possible states in the counter is going to be 2 raised to power n in case of asynchronous. Okay, in case of asynchronous, 2 raised to power n number of possible states we can have, right? And what is the modulus of the counter? Suppose see, out of 2 raised to power n, suppose this value is 16. So out of 16, if I am using only 10 states, right, then that will be known as the mode of the counter, right? So out of 2 raised to power n, if I am using only n number of states, then this is known as the modulus of the counter, right? If this is the suppose as counter, and the mode of this counter is m, and f is the frequency of the clock signal, then output frequency of this signal is going to be f upon m. And if you are cascading two counters, the mode of this counter is n and the mode of this counter is n, f is the input frequency, then output frequency of this is going to be f upon m into n. Okay, this is very important concept here, right? Asynchronous counter, if we are using only, see, if suppose this is a 3-bit counter, right? If you are applying clock signal only at this flip flop, and the clock signal for the rest of the flip flop is going to be the output of this flip flop will be used as the input clock signal for this one. So this is known as the asynchronous or a ripple counter. Okay, and this is going to be LSP, and this is going to be the MSP. This order is very important. Okay, don't forget it. And these are the, if you will, these connections will show you the type of counter that you are going to have. This is again very important. If it is a negative edge triggered flip flop, right? So if your Q is given as the clock signal, then it will be a up counter. If Q bar is given, then it is going to be a down counter. Like this you can solve it, right? And flip flops are always operated in the toggle mode. Okay, these are the few important points. You can go through these points. Okay, so this is an example of a synchronous counter. Here it is a positive edge triggered flip flop, and Q is given as the input, so this is going to be a down counter. Okay, this is going, and here it is a high, so when both J and K are 1, then the flip flop will operate in its toggle state, right? So indirectly we are using T flip flop here, right? So here Q3 is the MSP and Q0 is the LSP. So LSP will change, right? Like this. This is the timing diagram. This is the clock signal and positive edge triggered, right? So Q naught will continuously change. So the frequency of clock signal F, then frequency of F Q naught is going to be F by 2. Frequency of this is going to be F by 4, F by 8, F by 16. Here we have four this thing na, so possible number of states are 2 raised to power is 16. So this is mode 16 counter. Okay, so frequency is going to be this is the frequency. This frequency is going to be F divided by 16. This is going to be F divided by 8, F divided by 4, F divided by 2. So this circuit can also be used as a frequency divider circuit. Okay, next one is the synchronous counter. If separate clock signal is given to all the flip-flops, so you can see the output of all the flip-flops will change at the same time. Right here you can see an example. This clock signal is given to all the flip-flops like this. It is a negative edge triggered flip-flop. And this is for the, now this is a counter, right? This is the LSP and this is the MSP. Okay, it is a synchronous type of counter. All right, this is nothing but a T flip-flop only, right? Okay, because see, this is one, right? And the output of this will be given as the input to the next stage like this. Then this will like this. Okay, this is a synchronous counter output. Okay, decade counter, as its name says, we will have only C. We have digits from 0 to 9, only 9 decimal. So only 10 this thing will be required, that will count from 0 to 9 only. So the 10th is going to be 0 0. That's why it is known as, it is called as a decade. So the mode of this counter is 10 only, right? So after 1001 your counter will reset to 0 like this. Okay, here you can see clear. It is active low pin. If we will give 0 here, then only your these flip flops will reset. Okay, if we are giving 1 here, then it will not clear the outputs. Okay, so we have to give 0. That's why we are connecting here, right? So this thing is 1001. So after this your counter will set to this. So what I will do here, q3, q2, q1, q0. So this is 1001, right? 9. So after this the clear should be 0, so that it will make all the outputs 0. So I am giving here q3, this is q3 1, and here we have q1. Q1 is given now. So this should be 0 when both these are high. So this is q3 and q naught I will give here q naught. I will give q naught here. Okay. 1 into 1. So this is going to be 0. Now it will reset. Okay. This is the only possible case when both the inputs are, these two values are high. In other cases, the output of NAND gate is going to be 1 only, right? Right? You can see here. You can check here. Like this, you can have a modulo. Right? Next is ring counter. It is an example of, again, synchronous counter. Okay. So this is the circuit of a ring counter. It will count only these 4 stages. Okay. So the value of n is here. Number of useful states are 4 only. So the frequency is going to be f divided by 4, that is n, f divided by n. So if we have n number of bits, then we have n number of the different states. These are the states only. Okay, it is like a ring. Output is given back to the input of this flip-flop. Okay, pre for setting output to 1, clear for setting output to 0, like this. Okay. Next one is this is an example of straight. Next one is the twisted ring counter. It is also known as the Johnson counter, switch tail counter, walking ring counter, like this. So here in the previous case we connected Q3 to Q naught. Now we are connecting Q3 bar to G naught, right? That's why it is known as the twisted. So in Johnson's counter we have 2n number of useful states. Okay, so frequency is going to be f divided by 2n, output frequency, right? This theory you can go through with this theory, right? This is a circuit. Here I'm using D flip-flop. Okay, here again I'm using D flip-flop. But right now we are connecting this to this, so it will work as a toggle. T flip-flop, okay? This is the truth table, right? So these are the states here. One stage, two, three, four, five, six, seven, eight, right? So 2n, so 8, right? These are the useful stages. Here you can go through the differences, okay? This point is important, number of states. Okay, a number of unused states is nothing but 2 raised to power n minus this thing. Okay, 2 raised to power n, we have possible minus n. This is incorrect, 2 raised to power minus n. Here this is going to be 2 raised to power minus 2n. This is correct, it is incorrect. Okay, this is correct, this is correct. Okay, this statement is correct. Okay, as I told you, this can also be used as a frequency divisor. Now here you can see the circuit. So this is given here, right? Given back to this, f divided by 2, 4 and 8, like this. Okay, frequency division by 2 if you will use one circuit only, like this. Output will continuously change here. Okay, because D is nothing but Q bar. That's why it will always change this thing. Okay, toggle flip-flop. You can use direct this thing. All will perform the same kind of operation, just we are using the different types of flip-flop that will toggle the output. Okay, see here asynchronous counter, as I already told you. Okay, so these 4 waveforms you can have of different frequencies, right? Last one is the number system or the data representation. I will not discuss the numbers here, like the hexadecimal number system, octal, and like that. So this is going to be data representation. Okay. Now here you can see the flow chart here. Data representation. We have two types of this thing: fixed and floating. Right. In the fixed one, we have one magnitude format, and second one is the complement format. Right. So in case of fixed point, see if we have like 8 bits here, 6, 7, 8. So out of 8 I will use these bits for the, see if we have a number like this, right? So this is the real part or the integer one, this is the fraction. So I will use these 4 bits for the integer part, and I will use these 4 bits for the fractional parts. If this will not change, that is known as the fixed point data, right? This point is fixed. If I will use I will put this decimal point here, right? Binary point, sorry. If I will put binary point here, then I will have only 3 bits available with me to write the integer, and these 5 bits will be for the fractional parts. Now how we will represent is, one is the magnitude and other one is the complement. In the complement, see, first one is the unsigned and second one is the signed in the magnitudes, right? If we have we use this unsigned format only to represent the positive data, right? And if we have n number of bits, then how many this thing you can represent? The range is going to be 0 to 2 raised to power n minus 1. Now the next one is sign magnitude. So out of, suppose you have n number of bits, so out of n, one bit will be assigned for the sign only. If this MSB1, if this MSB1 is 0, then your number is going to be positive. If this bit is 1, so your number is going to be negative. And the rest of n minus 1 bits will be used for the data only. Magnitude to write magnitude. So the range will be this only, because out of suppose 8, 1 bit is assigned for the sign. So we are left with 7 bits. So with the help of 7, How many numbers you can represent? Minus 2 raised to power n minus 1 to this. The range for these two is going to be same only. For 1's complement and for signed magnitude. For 2's complement, it is this. Okay. Now the second one is the complement format. In the complement format, suppose we have a number like minus 6. If you want to write, okay, I will explain this thing next. Next is the 2's complement form. So you can write positive data using four formats, but to represent the negative data you have only these three formats: signed magnitude format, 1's complement and 2's complement, and these are the range values here. Okay. Next is the floating. Okay, I will discuss this thing in detail because this is very important. One question will definitely will be there from this topic. If you will compare, the chances are high that you will expect the problem from the floating point data. Okay, this thing is very important. Okay, now let's discuss this thing in little bit detail. Okay, you can go through these things. These are very easy. Sign magnitude I already discussed. See here. If we have plus 69, so how you will represent it? Using the 8 bits like this. So this 0 bit is for the sign, and this will show the magnitude, that is the 69. Here we have minus, so this is going to be negative data, and the decimal value of this binary is 69. Okay. Next one, 1's complement method. Okay, so in the 8-bit system, how you will represent plus 5? You will write the value of plus 5 like 101, and if these bits are 0, which means that this is going to be a positive 5 number. And see here, these values are 1 now, so which means that sign is negative. And this is the amplitude value of, oh, it's 1's complement, sorry, it is in 1's complement, I'm so sorry. Right. So see, if there is a number plus 5, so how you will write it? 101. Now I will put 0 because plus sign is there. Now how you will write minus 5? You will take the 1's complement. So how you will take the 1's complement? If we have 4 bits, so I will subtract this value 010 from this one. So 1 minus 1 0, 1 minus 0 is 1, 0 1. If this is the number and you have to find out the actual number, then you will see here sign is negative, which means that this number is going to be a negative number. Now to find out the actual number, don't write down this in the decimal form. Take the complement of this thing, 1's complement of this. So this is going to be 0101. Now you will read here, this value is going to be 5. So answer is minus 5. Okay, 1's complement is nothing but just replace 1 with 0 and replace 0 with 1. Then you will get you the 1's complement. So the limitation of this is that, because see, if we have 0 like this is plus 0, then how you will write minus 0? If you will take the complement, it will become, so this is minus 0. But actually we have no such plus 0 or minus 0. Now we have only 0 only. So that's why we are using the 2's complement method here. So in the 2's complement method, suppose we have plus 5. So I will write, this is plus 5, I will put 0 sign here. Now how you will write minus 5 in 2's complement form? What you will do, you will start from the right hand side. So whenever you will see the first one, see this is the 1, so I will keep this one as it is, and I will take the complement of the remaining bits. So here we have 0, so I will write down 1. Here we have 1, so I will write down 0 here. I have 0, so I will write down 1. And this one will be as it is. Now this number is in its 2's complement form. The 2's complement of this number is this. Now here you will see this is negative. So this is going to be a negative number. 1, so negative number. Now I will take the 2's complement again to get the original number. So again I will keep this one same, and I will complement the remaining one. So this is this. Now calculate. So this is going to be minus 5. Okay. Now see here, if a number, suppose we have plus 9. So how you will write it? 0 0 1, and I will put 1 0 here, right, for sign. Now how you will write minus 9? So I will take the 2's complement. Okay, again 1 0. Okay, leave it. I will take one more example. Suppose I have 10. So how you will write? 1 0 1 0. This is 10, right? I will put 1 0 for the sign. Now let's find out the minus 10. So I will take the 2's complement. So I will start from here. So 1 0. So I will write 0 as it is. Now this is the 1. This is the first one from the right hand side. So I will write it as it is. Now I will take the 1's complement of the remaining bits. So this will be like this: 1 0 1. Now this is the 2's complement representation of minus 10. Suppose this is given, now you have to find out this number. Binary format is in 2's complement form. Find the actual value of the number in decimal form. So here we have 1, so I will put negative sign. Now let's take the 2's complement. So I will start from here. So this is 0, so I will write 0 as it is. Here we have 1, so I will write 1 as it is. Now I will complement remaining bits. So this is going to be this. Now find the decimal value. So this is plus, this is 10. So answer will be minus 10. Okay, and this is the range. Okay. Now the last but not least, this is very important. Floating point representation. IEEE 745 standard. Right? So what I will do here, students, we use floating point method, this representation, to represent the large value numbers, like the value of your the mass of the earth, the value mass of the electron, because the power is like this na, 10 raised to power minus 19, 10 raised to power plus 36, like this. Then how you will represent these numbers? So if you will use fixed point method, then you will need large number of bits to represent these values. So that's why floating point introduced, right? So to write and this IS 745 standard is nothing but how you will represent these values, right? That will be decided by IEEE 754 standard. So let's discuss. So first of all, what you will do, suppose this is a number. First of all, you will represent the given number in its normalized binary form. Normalized binary form. So how you will represent is, this is the normalized binary form. Okay, this is the normalized binary form. What you will do, for sign you will use plus minus here, and I will put 1 here, plus sorry, dot. These are the binary values. Okay, these are the binary values. Okay, into 2 raised to power n. So this is n is nothing but it is known as the exponent, and this part is known as the, here this thing, significant. Okay, significant, right? And this is the sign here. So we have two types of formats: 32-bit single precision and 62-bit double precision, right? So here I will use 32 number of bits to represent this normalized binary data, right? So how you will assign these values? Okay, 8 bits for the exponent, 23 bits for the mantissa, right? Mantissa is nothing but significant only, right? So these will be decided by this IEEE 754 standard. Okay, now see here, in the 32-bit, we will use 1 bit for the sign, we will use 8 bit for the exponent, 2 raised to power e plus minus e, right? This sign can also be plus or minus, na, 2 raised to power plus or minus, and 23 bits for the fractional part, this thing, 1 dot onwards. Okay, so here you can see the number is represented like this. Okay, in the double precision method, 1 bit for the sign, 11 bit for the exponent, and 52 bit for the mantissa, right? And here I will use the bias representation for the sign of the exponent. For the sign of exponent, I will use the binary representation. So how you will represent this value? 2 raised to power n. Here I am assigning 8 bits na, right? So the value of the bias is going to be 2 raised to power n minus 1 minus 1. So here the value of n is going to be 8, so 2 raised to power 7 minus 1. So this value is 128 minus 1. So the bias value is going to be 127. Okay, so the stored exponent value will be equals to real exponent value plus here this thing, bias value. Okay, now let's do it. In the 64, 11 bits for exponent, 52 for mantissa, like this. Now let us take the example. See, why e raised to power this thing? This is the stored value. Yes. Okay. So let's write it. Minus 13.25 using the 32 bits. So how you will write? Suppose these are the bits. 32 number of bits. So here we have negative sign. So I will put 1 here. Right? So first of all, what I will do, I will write down this 13.25 in the binary form. So how you will write 13? How you will write 13? Let's do it. 13 is going to be 10 plus 10 plus your this thing, 10 plus 8 plus 5. So this is going to be 13, right? Dot. How you will write represent 25? 25 into 2, 0.25 into 2. So this is going to be 0.50. So I will write 0 here. Then 0.50 multiplied by 2. So this is going to be 1. So this is going to be 0, 1. Now let's represent this into normalized binary form. So how you will do? I have to shift this point here towards the left, right? 1.10101 multiplied by, I am shifting this by 3 values in the left hand side. So I will write 2 raised to power plus 3. Okay, now you will fill this thing. So sign is 1. Now this is the fractional value. So I will write 1 0 1 0 1. Remaining bits will be 0. Okay, and how you will fill this thing? Plus 3. As I told you, how you will write it here? Stored value will be equals to 3 plus 127. So this value is 130. So I will write down the binary representation of 130, right? Okay, so wait a second. Right here you can see 1 0 1 0. This is this, right? This is for the sign. Now let's calculate it. This is going to be 1 plus 1 2 3 4 5 6 7. So 2 raised to power 7. So this is 128 plus 129. So this value is 129. So how you will write? 127 minus 129. This is the value of actual exponent. This value is 2. And here I am getting this value as 3. There is a mistake here. This value should be like this. 129 I will, 130 I will write here. So this is going to be this. Okay. Now let's take the next problem. Suppose the number is 32. For first bit is sign bit, 8 bits for the signed exponent, 23 bits for the fractional part, and leading 1 is not stored and 1 is always normalized number referred to as hidden. So minus 53 is normalized as this, right? So minus 53.5 can be written like this. Okay, this is the fractional part and this is the integer part, right? Minus sign here. Now how you will convert this into normalized form? So I have to shift this point 4 places, 1, 2, 3, 4, 5. So I want to have this here, right? So I will multiply by 2 raised to power 5. So here the value of exponent is 5. Here the value of exponent is 5. So this is the sign bit. This is the mantissa, that is your fractional part. Okay, this value. And how you will fill this value? This is going to be, wait a second. So students, how you will write this exponent value? So this value is 5. So the stored value is going to be 127 plus 5. So this value is 130. 130. 132. So I will write 132 here. So it is, see, it is correct only because we have three possible ways to represent this exponent. So we will use in IEEE 754 standard, we will use the bias representation method here. Okay, so how I will write 132 here? You will find the binary. So this is going to be 2 raised to power 7. That is your 128 plus, and so 28 plus 4 will be. So how you will write 4? 4 is going to be 1 0 0 like this. Okay, 0 0 0 1 2 3 4 5 6 7. So this is the exponent value here. 1 4 times 0 1 double 0. Okay, this is going to be the exponent value here. Okay, in the bias representation method, here I'm using, I think here they are using the one's complement or the signed method only, I think so. Signed magnitude method, right? It's not clear. So this is the possible smallest number here using the 32 bit 2 raised to power minus 126. Okay, and if you will talk in the terms of decimal value, then this will be the decimal value, and the largest one is going to be 1 point all the ones 2 raised to power 127. Okay, so this will be the maximum value that we can have. Okay, similarly for the, okay, I hope this is clear to you all. This floating point is very important, students. Okay, I will take few more problems from here. Don't worry. So you can also represent in the decimal. See, 32 bits are given to you. Okay, suppose these are the 32 bits. 1 bit for the sign, then 4, 5, 6, 7, 8. And these are the 32 bits for the, sorry, 23 bits for the fractional part. These are the 8 bits for the exponent. So how you will represent it into your hexagon form? Suppose these values are like this. Remaining all are 0 only, right? So you will make a group of 4 ones like this. So 1 0 1 0 is going to be 0 cross, you will write here. So 1 0 1 0 is going to be 8 plus 2 is 10. So how you will write 10 in hexa? A. Now make a group of these 4 ones. So this is nothing but 14 only. So how you will write 14? D. No. A, B, C, D, E. Yes, E. I will write an E here. E is for 14. Next 4. So this is going to be 5. So I will write 5 here. Next, all the bits are 0. So total how many this thing will be there? 8. So I will write down 5 zeros here. because 8 into 4 is going to be 32 na. To represent hexadecimal number we use 4 bits. Yes, so if this is in this form, right, then how you will fill this thing? 32 bits, you will fill it like this. Now from here you can write down the number in the binary normalized form. Okay, from that you can find the value of hexadecimal number. Oh, sorry, decimal number only. Okay, so the most important is 32 bit only. 64 sometimes they can give you, but I think it is not going to be there, right? But the form, you just remember the how they will sign it. 1 bit 11 and the remaining one for the mantissa. Next, I don't know whether these two topics will be there or not, because they haven't provided the detailed. So I will cover this thing also. So binary coded decimal. So as its name says, decimal code. So we will have only digits from 0 to 9 only, right? So to represent each number, each decimal number, I will use 4 bits. I will use 4 bits. Suppose you have to represent 5, then I will write it like this: 0101. 10, I will not represent it like this: 1010. No, this is the incorrect representation for the BCD code. How you will represent 0? Separately you will write 0 using the 4 bits, and separately you will write the 1 using the 4 bits. Sorry, like this. Okay, similarly, if you have the number 943, then separately you will use 4 bits to write 3, 4, and then 9. So this is the BCD here, this thing, binary coded decimal form. Okay, and it is also known as the 8421 because of this thing only, right? Now next one is the XS3. What you will do, first of all you will write down the given number in the BCD form, then you will add plus 3. Okay, then you will add 3 to each coded number, like this is the representation now. So what you will do, you will add plus 3 here. So how you will add? This is going to be 3 plus 3 is going to be 6, so you will write it like this: 6 plus 3, so you will write it like this. Okay, like this you can solve it. Okay, so this is known as the unweighted code, and it is a self complementary code, because see, if you will find out the complement of 9 na, then in the binary form, if you will find out the ones complement, then you will get the value of this thing, minus 9. Okay, like this you can solve it. Here you can see ones complement of the XS3 is the XS3 code for the nines complement of the corresponding decimal number. Sorry, not minus 9, nines complement of the corresponding decimal number. So what is the nines complement of 9? 9 minus 9 is going to be 0. Okay, let us take an example here. Suppose I have 1, right? This is 1, BCD 1. And what is the XS3 representation of this one? Plus 1 4, so this is going to be 0 1 0 0, right? This is this thing. Now I will find out the nines complement of this one. So nines complement of this one is going to be 8, right? Nines complement of this is going to be 8. Now let's take the complement of this one. So this is going to be 1011. So this is nothing but the XS3 representation of this 8. So how you will write 8? 10008. This is 8. Now XS3 code of this is going to be this only, 8 plus 3, right? So if you will perform the nines complement on this number, then if you will directly take the complement of the XS3 code, its equivalent XS3 code, you will get the complement of this thing. This statement is very important. Generally we will use this configuration only in the arithmetic circuits. Okay, see, we will never perform this thing. Why we use the complement? Suppose if you want to, like this, 3 minus 2 you want to do, then what you will do? You will do 3 plus 2 then minus 2. So you will take, either you will take the help of here this thing, complements, or you will take the help of unsigned magnitude representation to write this minus 2 in the binary form. Okay, so students, that's all for this session. Okay, I tried my best to cover all the important topics quickly, right? And if you have any doubt, then you can write down in the comment box. I will definitely read your comments. Okay, and if you have liked my session, if you find this one as your this thing your useful for you, then please like and subscribe this thing. Okay.